Okay, so let us start again with root test. We have already seen the statement, but today we are going to prove it. But briefly, let us once more, before we start the proof, go through the statement. We are given a series of real numbers and alpha is the limit superior of this sequence whose nth term is the nth root of the absolute value of an, where an of course is this term of the series. Now there are three conditions. If this limit superior turns out to be less than 1, then our series is absolutely convergent and hence conditionally convergent. That means it's just simply convergent. On the other hand, if this limit superior is greater than 1, then the series is conditionally divergent, which just simply means that it is divergent and hence it cannot be absolutely convergent. But if this limit superior is equal to 1, then we cannot assert any conclusion. There are series where this value is 1 which are convergent, but at the same time there are also series where the value is again 1 but they are divergent. Okay, so let us now see the proof. The proof is not very difficult. We just have to recall the elementary properties of limit superior, and because of that we have to recall some previous results that we have already seen and we proved also. Okay, so one by one we tackle the three parts. Proof. Suppose first that alpha is less than 1. So that means we are in part A. Then we can find a real number epsilon such that okay, now but how are we claiming that we can find a real number epsilon such that this thing is true? Perhaps I should instead of just directly writing this, I should also include this fact. Not just epsilon but a positive epsilon. And another thing that I should mention here is that alpha itself is greater than or equal to 0, and due to the positivity of this epsilon, alpha plus epsilon will be strictly greater than alpha, and this is less than 1. Now we need to address two things here. The first one is, how are we getting this? How is it that alpha is a non-negative real number? And the second thing is, what about this epsilon? Where is this epsilon coming from? So let us first see why alpha is non-negative. So what is alpha? Alpha is by definition the limit superior of these terms, or the limit superior of a sequence whose terms look like this. So that requires us to go back to the definition of limit superior. At least we should know, or we should be able to recall what limit superior is by definition. So that thing, if you recall, is just simply this. You look at all the terms in your sequence. Things are starting from m, right? M is some integer we don't know, we don't need to know also. Oh, okay, wait, but there is a, if we do not say what n, I think I said something about this in the previous video itself. Because we are considering nth root, so n needs to be a positive integer. So the sequence that we see here is actually this sequence. This sequence. The nth root of the absolute value of an, where n varies from 1 to infinity. Now if it happens that m itself is some positive integer other than 1, then you have to start from that positive integer. But say, just for the sake of understanding and simplicity, that this m is in fact just 1. Okay, it is not something fundamental to what is happening. I mean, the value of m is not something fundamental to what we are now going to see. So for the sake of convenience and simplicity, let us just assume that m is 1. Okay, so now if we consider the terms of our sequence, the 1th root of the absolute value of a1, the non-negative square root of the absolute value of a2, and so on, like this. This is our sequence of which we are considering the limit superior. So the thing is just this, if you recall. Say this sequence is denoted by Bn, where Bn is of course this. Then what is your B1 plus? B1 plus is the least upper bound of the terms of this, I mean the entire sequence. That is, it is the supremum of Bn where n is greater than or equal to 1. We can write in short like this. What is B2 plus? B2 plus by definition, here I am using the notation that we already saw when we were discussing these things, okay, in the 6th chapter I think. Now B2 plus is the supremum of all the Bn's where now n is starting from 2. That means we have removed the first term of the sequence. Still we are left with a sequence. So that sequence also will have a supremum. That supremum is B2 plus. And you continue finding the other classes, the other suprema like this. And you get a sequence Bn plus, where n itself is varying from 1 through infinity. Now, then you calculate the infimum of this sequence. That means you calculate the infimum of Bn plus as n varies over all positive integers. This by definition is alpha, limit superior. That means this is the infimum of the suprema of your original Bn where n is starting from n. So now if you look at the special, because our Bn is not just any sequence but rather this particular sequence, you can see that all the Bn's are non-negative, simply because the real number of which we are calculating the nth root, that is a non-negative real number, and the nth root by definition is also non-negative. So that means this is a non-negative sequence. And why see, when I am saying that all these terms are non-negative, that is, this is non-negative, this is non-negative, that's what we are saying here. That does not automatically mean that these are real numbers. They may be any one of them, maybe plus infinity also, that possibility is also there. But still, by non-negative, I just mean that these quantities, all of them are greater than or equal to 0 in the extended real number system. Any one of them may be plus infinity also. Of course, because of these inequalities, none of them can be minus infinity, but still that possibility is there. Okay. So now, because they are all non-negative or greater than or equal to 0, whatever infimum this sequence has, that will also be non-negative. Do you see why? Because due to the presence of these inequalities, 0 becomes a lower bound of this sequence of suprema, whereas the infimum is by definition the greatest lower bound, and 0 is just only one lower bound. So the infimum will be greater than or equal to 0, and that's how we are getting the fact that alpha is itself non-negative. Okay, so that means we now know where this first inequality is coming from. Now if we manage to choose one epsilon such that epsilon is positive, forget about this third inequality for the moment, you just think of the middle one. If epsilon is positive, then alpha plus epsilon of course is greater than alpha. So the middle one is also justified. But where is this thing now coming from? That is, how can we choose one such epsilon? It is rather easy. So this part we understood. So I can just wrap it up. In fact, the author himself writes, we can choose epsilon to be equal to 1 minus alpha divided by 2. What happens if we choose that? Let's just do the calculation quickly. Alpha plus 1 minus alpha divided by 2 gives us what? If we simplify things, 2 alpha minus alpha will be alpha, and plus 1 of course will be there. So 1 plus alpha divided by 2. Now 1 plus alpha divided by 2 actually is less than 1. Why? Because if you multiply on both sides by 2, you get 1 plus alpha less than 2, which is equivalent to the inequality alpha less than 1, which is what we have. And we can of course come from here to this one also. So that is why this is, we can take this value of epsilon. But one more thing is there. This epsilon, note that in spite of being a favorable epsilon which gives us this inequality, but it is positive also. That is because alpha is less than 1. So for this value of epsilon, you will, we can make it work. But other values of epsilon also will exist, which one may choose. We just need one epsilon, and that's it. Okay, now it's time for us to recall one of the basic properties of limit superior. And that property is this. Next, I'm going to just roughly write it. and that property is this. Say you have a sequence Bn and say L plus is the limit superior of Bn. Now if you have an extended real number x which is less than L plus, if you get an extended real number x which is less than the limit superior of this sequence, then there exists some integer n greater than or equal to this starting index m such that the terms of your original sequence Bn are all greater than x. Am I saying it correctly? Let me just see. These things become so confusing so easily. If x is greater than L plus, then An is, oh, so we are using this one here. See, I have already made a mistake. What I was thinking I was saying is not the one that actually I am supposed to say here. If x is greater than L, then there exists such a stage such that Bn will be less than x for all indices n greater than or equal to n. Confusion arises because there is a similar one which is the other thing, the other type of inequality, that is if you get an extended real number less than L plus, for that also there is something. Okay, so that means if our x, this extended real number, is greater than the limit superior of our original sequence, then the terms of the original sequence will become less than x starting from some stage. Some n onwards this will happen. Now here we have one such x for our limit superior, and that x is 1. And in fact, not just 1, we are not going to consider this 1, but rather we are going to consider this alpha plus epsilon. You imagine alpha plus epsilon in place of x, and your alpha is your original limit superior of that sequence where you have absolute value of n and all those things. So now we can apply this result, and this result is we will write things down, but it is proposition. See, if you are wondering, it is proposition 6, 4, 12 part A. It is that proposition which tells us, which gives us the fundamental properties of not just limit superior but limit inferior also of sequences of real numbers. Okay, so let us now proceed. Now y, so now we know what we have to write. Proposition 6, 4, 12 part A. There exists an integer n greater than or equal to m such that the nth term of our sequence, which now is this, is less than the x that we are considering, which is this. Alpha plus epsilon, and this will happen starting from some stage, and that stage is this n. for all indices n greater than or equal to n. Okay, so that means all the terms of our original sequence of which the limit superior is alpha are less than alpha plus epsilon starting from this stage. In other words, our sequence of which the limit superior is alpha is eventually less than alpha plus epsilon, right? This implies the absolute value of an is less than the nth power of, if we take nth power on both sides using the basic rules of exponents and along with inequalities, all these things we already got before. We get this for all n greater than or equal to n. Okay. Now you will realize why we did this and why we did not just simply work with this inequality itself. Because do you see one thing now? Now we can say something about the convergence of the original series, because we have obtained some inequalities which allow us to compare the original series with another series, a geometric series. Our original series, of course, is this. This is our original series. But we, of course, have got these inequalities not for all the terms, but rather for this series where our index starts from n. That's not a very big problem. And the corresponding other series I am talking about is this, summation alpha plus epsilon whole to the power n. Okay. Now here there are some subtle things that one needs to address before one can in fact use this series. You may note that still this n may create a problem, and the problem is that this n actually may be a negative integer. We really don't know, because we don't know m, so we also don't know what n is, or rather what its sign is, whether it is positive or 0 or negative. We have no idea about that. So if our n, if this capital N, say it happens to be -2, okay, then your series looks like what? +1 plus alpha plus epsilon plus, it will then of course continue. Now this is not exactly a geometric series. I mean, it is, but the thing is that here things have started from -2, so this part is creating problem. The rest is of course our familiar geometric series. So what do we do? What we do is that we work only with this part, and you can see that this part actually is a convergent series. Why? Because this thing, the main thing in a geometric series, which is like this, 1 plus r square, etc., we know that this series is convergent if and only if the absolute value of r, well, not exactly the absolute value of, so I mean more specifically this, in particular if r satisfies these inequalities, and such inequalities are available here. with alpha plus epsilon in place of r. So that means this part of the infinite series is convergent, but by the properties, the elementary properties of infinite series, we know that if this part is a convergent series, then adding two more terms or finitely many more terms does not make a difference. It does not change convergence. You still get a convergent series. That means that a total series is convergent if and only if the tail end is convergent. One such thing is there. If you go back to the basic properties of infinite series, there you will see that the proposition or theorem, whatever it is, it has a number of parts. One of those parts has this thing. Okay, so that means if our n is negative, then we will deal with this series like this. But if our n is positive, say, and it is say somewhat large, say it is like this, n is equal to say 2, then our geometric series that we will consider here will look like this, which is also not the full geometric series. Here in fact we are short of terms, these first two terms, but again by that same series property, this is convergent if and only if the original one is convergent. Now because we have these inequalities, the condition for convergence is satisfied for the original one, and so this other series, which you may call a sub-series of this one, is also convergent. That means after all, we don't really have to think about what this n is, where things are starting from, and that is because whatever this n is, we will have to adjust only finitely many terms in the beginning, which do not affect convergence or lack thereof. Okay, so we are going to next write like this. Actually, by starting our things with a general m, we are getting these problems, which are really unnecessary. But anyway, that's how things are in the text. So what can we do now? Since alpha plus epsilon lies strictly in between 0 and 1, the geometric series that means our original geometric series where things really start from 0 is convergent. So by that property of infinite series, and which is proposition 7 to 14 part C. So by proposition 7 to 14 part C, this series is convergent. It does not matter whether this series has more terms or less terms than the original series. Whatever the case is, those excess or deficit terms are finite in number. That's what matters. Okay, so this series is convergent. Hence, by these inequalities and the comparison test for convergence of series, so by the comparison test, the series this is convergent. Keep in mind that whatever we have in these inequalities, we have to take those exact things in the series in order to apply the comparison test. So like here we have not an but absolute value of an, so the comparison test along with these inequalities would tell us that this series is convergent, not this one. Okay, I mean, of course it will also be convergent, but that comes afterwards. First we have this. Hence, but again by proposition 7 to 14c, the beginning index does not matter. Where the index begins, that does not matter. Hence, by (7 to 14c), our original series, its absolute version, where things start from small m, is convergent. And convergence of this just simply means what? That our original series, the one which has only an's, is absolutely convergent. And so this is absolutely convergent and hence conditionally convergent also. So this is part A that we have proved, but I think I need ink, so let me just first refill and then we will turn to part B. Now we are going to prove part B, and in part B the inequality, I mean our hypothesis inequality, is the opposite one. This time around alpha is greater than 1. So we have to use the other property of limit superiors that which I got confused, where I got confused in between that one and the one that we used here. Okay, so next part B. Now suppose alpha is greater than 1. Okay, whatever. Now to use this one, we do not need to do anything, like we do not need any epsilon or anything here. We can just use it as it is. So the result that we will be now using is this other thing. Again, Bn is a sequence of real numbers and L plus is still the limit superior of Bn. Now if it happens that some extended real number y is less than L plus, then for every integer n greater than or equal to m, there exists some integer n greater than or equal to this n such that Bn is greater than y. That means no matter what you choose this capital N to be, you will get a stage or some instance after that n such that your term of the original sequence, the corresponding to that n, that is Bn, is also greater than y. Or speaking very loosely, you can say this entire thing like this in words. If y is an extended real number which the limit superior of Bn exceeds, okay, if it crosses, if it surpasses y, if it exceeds y, then the terms of the original sequence also exceed y infinitely often. That is because for each of your choice of n, you will get a little n for which this thing, this exceeding property is true, that Bn exceeds y. It's not, I mean, see, do you see the difference between this one and that one? There, an inequality turns out to be true starting from some stage and then for all Bn. So something is true there eventually. Here, however, that is not the case. Here, something is happening infinitely often, not necessarily eventually. Okay, so that distinction is there. So we can just simply use this one directly. Now, by what is the number? Proposition 6, 4, 12, but now this is not part A, this is part B. For every n greater than or equal to m, there exists n greater than or equal to n, where it is understood that these quantities are integers, okay, not mentioning integers separately, such that but what is our, we don't have Bn, instead we have these nth roots. These are greater than 1. So the role of y is played by 1 here, and alpha of course is L plus. That is, for each integer n greater than or equal to m, there exists n greater than or equal to n, such that if nth root has to be greater than 1, then the number itself has to be greater than 1. So do you see what we have obtained here? Now we don't have nth root or anything. Now we are just simply looking at absolute values of the terms of the series, or rather we are looking at this sequence. Now what we are stating here, it has implications. What we are stating is this: it does not matter how far down the sequence we go. Say we choose our n to be m plus 2. Then what we have written here is just simply this: beyond m plus 2 there is some n for which this absolute value is greater than 1. So no matter how large you take this n, capital N, you will always get a still larger n. Well, of course this n may be capital N also, but starting from that stage onwards you will get some index value n, which will make this absolute value greater than 1. So do you see that the sequence absolute value of an cannot converge to 0, because you cannot make things smaller and smaller, like what we see in case there is convergence to 0. Then after some stage things will get smaller than say 1 epsilon. Then you choose another epsilon, you will get another stage after which things get even smaller than that epsilon. That however is not possible here because of the presence of these infinitely many problems which prevent the size of an, it does not let the sizes of an go down. They will never go down. In fact, infinitely many terms of this sequence, in fact this sequence cannot be made small. They will be greater than 1. So how can they be made small and close to 0? And because of which the sequence absolute value of an does not tend to 0. And that just simply means that an itself does not tend to 0. Or you can think of it like this also. A better way of concluding this entire thing is given by Tao himself when he writes these next lines. So in particular, these inequalities mean that the sequence an, where n is varying from capital N, is not one close to 0. Why? Because the distance between this absolute value of an is nothing but the distance between an and 0. A sequence being one close to say 0 just means that the distances of all the terms of that sequence being less than or equal to 1. Here however that is not possible, and this is not possible for any choice of capital N. Is not one close to 0 for all n greater than or equal to m. So our original sequence where things start from small m is not eventually one close to 0. The impossibility of finding such an n tells us that nothing is ever going to happen eventually. That eventuality does not occur at all. that starting from that stage onwards things are settling down towards 0. No. Hence, the sequence AN does not converge to 0. Whether this sequence is itself convergent or divergent, that we don't know, but whatever the case is, it does not converge to 0. Even if it is convergent, the limit is not 0. But then by 0 test we can say that our original series is not convergent. So because what does the 0 test say? It says that if you have an infinite series of real numbers and it is convergent, then the sequence of its terms should converge to 0. So that means equivalently, if this sequence is not converging to 0, then the original series cannot be convergent. So by the 0 test, the series is divergent or conditionally divergent. Conditionally divergent and divergent they mean the same thing, and because of which it cannot be absolutely convergent, because otherwise it would have to be convergent, and that is just your part B. And part C is it is not provided by the author, we have to do it. For alpha equal to 1, see the third exercise. (753), which however we will solve only when we start solving the exercise. Before that there are other things. Okay, so now we have not really completed, but in this sense we have completed the proof of the root test for convergence. You can use the root test, and there is one other thing that may be helpful. If you encounter a series of real numbers and say you want to use the root test, of course that requires you to calculate this limit superior. Now if it happens that this sequence actually is convergent and it has a limit, then of course it will have a limit. Then by the properties of limit superior, limit inferior, in that case the limit superior will coincide with the limit of the sequence. So if your sequence for the given series is convergent, then instead of limit superior you can just use limit, that's all. If this limit is less than 1, then your series is absolutely convergent and hence also convergent. If it is greater than 1, then it is divergent. Whereas if it is equal to 1, then we will see that we actually cannot conclude anything. We are not in a position to conclude anything. Besides the root test, you also have the ratio test, of course, where things are easier because the ratio test does not involve nth roots but just ratios of terms of your series. So that we will see in the next video, how one can there are some inequalities that link these types of roots with these types of ratios, using which there is a lemma which allows us to prove that link, that those inequalities, and using that lemma we will be able to get the root test which is easier to apply. It is less powerful than the the ratio test which is easier to apply, which is less powerful than the root test, but things are easier and nicer. And then when we complete things in the exercises, we will successfully use these two tests to check the absolute convergence of quite a few types of series. Okay, so with that I end this video. If you want to say something about these things, you can write in the comment section below, or you can mail me at my address. The link will be there in the description. And this so the next video, today is, what is the day today? Today is Sunday, no? So the next one is on Tuesday. And on Tuesday again, because we have already we have completed graph theory once more. So the next is again permutation groups from Herstein's group theory, Herstein's topics in algebra. So until then, this is me, Lucifer, from a mathematical room. So see you on Tuesday. Have a nice night.